this example, we will look at how we bias the current source load. So this is also current source. So to bias that, we have the current meter like this. For the NMOS bias, we use the similar biasing scheme that we used before. And for the PMOS, we have additional current source and mirroring device. Okay. In this case, we have additional current IB is required to bias M2. So IB2 is necessary to bias M2, right? To remove such kind of a current consumption, we can use the self-biased load shown on the right. So in this case, we have a large RG so that the bias voltage, gate voltage, is determined by diode connected the structure. In this case, the DC current through the RG is always 0 amps, so the voltage drop is 0. So we use that RG to generate the proper gate voltage to flow the same amount of current as in the M1 drain current. So if the ID flows, same ID flows through the M2, right? This is a self-biased load. So in this case, this signal comes in here. So by having large RG and CG, large capacitor there, so this is low pass filter. So if we remove that, if you have a large RG, so that lower the bandwidth, if you have a lower bandwidth, so that the signal doesn't pass this RG, then this one is a small variation there. So this is, it looks like a DC voltage there. So it becomes similar to the left hand side biasing. So in this case, you require you need the large RG here. Okay. So your signal frequency must be what? Signal frequency must be higher than low pass filtering cutoff frequency 1 over RG is EG, right? So that the signal doesn't pass this RG. What happens if the signal moves the same as the drain voltage? Then it becomes the for WC is a lot less than bandwidth there, meaning that the signal moves the same way, the same voltage is shared across the gate and drain, that it becomes equivalent to that just diode connected load. In that case, the output impedance becomes 1 over GM, right? For this self-bias scheme, if the signal doesn't pass through the RG and filtered, then the output impedance at the interest of the frequency, that is just the RO, right? ROP. So this is quite the nice way to self-bias. Okay. Drawback of the self-biased load shown explained in this figure here is the limited swing range. In some cases, you may end up having smaller output swing range. For example, when you have like this, then we have a VTH plus V overdrive voltage, right, across the source and gate. So the voltage swing, it can go up to for example, let's say V out. So V out range would be what? The maximum V out would be VDD minus V overdrive, right? And for the lowest voltage will be, so if we have a similar overdrive for the PMOS and NMOS, let's say, so M1 also have a VGS, VTH plus overdrive, so the minimum voltage can go down is overdrive voltage of the M1. So for the upper part is overdrive of the M2, right? So this is the range. So proper bias, the optimal common mode bias level will be the exact in the middle of this range, so that the this is the optimum. But in reality, in this self-bias load, the output common mode is biased where that would be VDD minus VTH minus overdrive, right? So that's gonna be the VDD minus VSG of the M2, right? So that's gonna be the actual biasing, output biasing point. But the optimum would be VDD minus V overdrive of 2 plus V overdrive 1 over 2, right? So there is some little difference or discrepancy between optimum bias and the real biasing point. So if you want to move that output common mode biasing common mode voltage, we may introduce the IG there. It may pull down or pull up current going into that IG, so that we can move up and down the output voltage. So this kind of IG create the voltage difference. So in this example, IG create the voltage drop over RG, so IG times RG, so that we can shift or up or down by the amount of IG current. So IG can be pull down current or sometimes pull up current, depending on your output situation, or right. So in this visualization, in this example, so the typically previous case, output common mode is VDD minus VGS 2, VSG2 here, right? So that it can go down by this level is overdrive of 1, right? The lowest peak is from here to overdrive, but it can go up by the same amount, right? In this case, you have the maximum output peak voltage would be VDD minus overdrive 2, right? VDD minus overdrive 2. So in this case, the output common mode is skewed down near to ground, so we have to move it back up, so that by having proper IG times RG, we can move the output common mode level in the middle of the output full scale range, so that we can increase the output swing range. Okay. In case this original input common mode level, if that is near like this, near upper range, for example, like this, and then moving, if that it might be limited like that, so in that case we use the pull up current there, so that the output common mode can be lowered. By having pull up current, we can have a voltage drop plus minus voltage drop across RG there. We can move back to in the middle similarly, right? In complementary CS stage, amplifier here. How we bias this properly. This is a very high gain amplifier. This is RO1 and RO2. This RO1 and RO2 are similar, so we have very high gain. So if your voltage biasing is a little bit off from the optimum, for example, then your output common mode will be stuck to VDD or ground. For example, like this kind of a characteristic, V in and V out, your biasing point would be exactly in the middle of this steep curve. So the slope of this curve is the gain of the amplifier, right? So it would be difficult to properly find the accurate voltage to place this kind of in the middle. To do that, we use the self-biasing scheme like the RF that will always bias that to be same voltage, like this kind of a biasing, and this kind of a equivalent circuit can be considered because at biasing level we can assume that there's no current flow between through the RF. Okay, so no voltage drop across the RF, 0. So it can be considered that like this situation. In that case, by having this electrical equivalent model, we have a V overdrive 1, VTH plus overdrive 1, VTH plus overdrive 2, properly generated for the different size here, and P and N. For any size there, you will find the right voltage, overdrive voltage, so that this one ensure M1 and M2 in saturation, right? But the problem is the amount of a current, bias current, is kind of a is sensitive to PVT variation. Why? The current level depends on the size mismatch, and the current level, current ID will change for the different VTH, for the different size, and for different temperature. So in some application where the low power consumption is very critical, in that case you wanna limit you wanna have the constant current consumption. In that case, we can add the current source at the top like this. But the problem is with this just simple current source, and this node is high impedance, so that for the input voltage variation, we would not have a proper VSG variation on the PMOS. This without C1, this structure looks like a source follower. So for the input variation, it will track the source node will track the input. So the VSG will remain constant, so that current amplification doesn't happen. To have a to knock down the signal component on the source node, we can have a like small variation by having C1, so that can be AC ground. So the equivalent similar gain can be achieved by by forcing that source node to AC ground. This can be done by adding large C1. Now the biasing is done properly. Now how we add the input can be added by large C-in. So by having the C-in, we can isolate the input common mode voltage and output common mode voltage, right? So isolate V in, V out CM voltage. So this gives us a more design freedom to change the color mode on both sides. More design freedom. Another requirement for sizing for AC coupling at the input, this looks like we have a finite impedance G in, so we have a C, so finite impedance and C result in the high pass filter, so the signal must pass through this capacitor properly for the given signal of interest. Signal frequency, we have to pass the signal. So the bandwidth of the input network, so for example, can be determined by the input network C in and G in. So input side we have a bandwidth of 1 over C in times G in. And this side, this node C1 must be large enough. How much large enough? At signal frequency 1 over GM2 here, looking down is 1 over GM2, and impedance of a C1 is SC1, 1 over SC1. That would be at lowest frequency, the impedance is high, so 2 pi, let's say omega min times C1, that would be the minimum largest impedance seen by C1. So comparing 1 over GM2 versus 1 over C1 mean, omega min, so that the 1 over C1 impedance seen by the capacitor must be much smaller than 1 over GM2. Similar requirement can be seen on the input side. So the input minimum signal frequency, at the minimum signal frequency, impedance of the C1, C in must be much smaller by impedance seen looking into this amplifier, that is the G in. Okay. Common gate amplifier bias shown in here. We have IB. This will create the voltage drop across RB. That would be IB times IB. And then we have if the same size of the device, W over L and W over L, then we will share the same gate voltage here. So this MB will have a VTH plus V overdrive between gate and source. If the RB and RS are same, then we will have the same size and same gate voltage that will create the similar current by having RS equal to RB, right? So this will have RB will flow same current. So this is kind of a biasing based on the RS, RB, and IB and device size. So if you wanna reduce, in this case, we wanted to bias the common gate amplifier shown on the left, but the current consumption on the biasing circuit is the same. So we may scale down the biasing network. Biasing circuit. How? So if you want our target biasing would be, let's say, if you wanna have a starting from here, ID current that will flow that through that RS, that will set up RS times the ID, and then for the given size of the transistor we'll have a VTH plus V overdrive, right? So now we wanna have a biasing network, let's say 10 times smaller biasing current. We would draw that W over L times 1/10, so 10 times smaller than main circuitry, and also on the resistor network. That would be how much? 10 times larger resistor in this case, so that the 10x lower current. For the 10x lower current, we show that the same voltage drop across the RB, right? Now we force that ID over 10, right? So this is how you bias and how you choose the device current and value and device size. Once you finish your main common gate amplifier design, you can always generate your biasing network and properly scale down for current saving. This kind of biasing has a negative drawback. One is it relying on the voltage drop across the voltage on this X node is sensitive to RS. So if the RS change a lot, then the overall gain changes. So this circuit, the gain of this circuit, the circuit is sensitive to register variation, right? So register very sensitive to RS and RB variation. Right, that will cause what? The gain AV changes, and also output signal range also changes. Right? Another way to bias the common gate is, instead of relying on the resistor, we use the current meter shown in here, so that we can reliably replicate the current, and also voltage drop across the VDS shown in here. It can be maintained low regardless of the current level, like so if the for the resistor voltage drop, if you increase the current, the voltage across the resistor is directly affected. So VR equal I times R, right? But for the voltage across the VDS is kind of less sensitive to IB current variation, because as you know that the voltage VDS can have a large range of the voltage can be supported for the different amount of a current, right? ID. So this one we can maintain X properly, so that the ensure that the output signal range is large enough. If you remember correctly, output signal range, you can find that the maximum voltage will be VDD and the minimum would be what? VB bias minus VTH, right? In that way, the M1 will be in saturation, right? And also there is a limit for the VB, so VB must be greater than what? So overdrive of the M2 plus what? VTH plus overdrive of M1, right? In that way, so we have the VB range. By having this requirement, we can ensure that M2 in saturation. Okay, now the question is how to generate the VB properly to ensure that this requirement. For generating VB, we may choose to use that just diode connected device on here, but this will create large voltage Vx node voltage. So we wanted to save the output signal range so that they properly generate the VB by having this high swing cascode bias. In this way, we can have the proper value like VOV2 and plus VTH plus OV1, so VB, we generate the VB in a way that how much V greater than overdrive 2 plus VTH plus V overdrive 1. So if we generate this much of VB and we use that the diode current meter like this, we can generate the current source. The reason why we have the M3 in that diode connected device on MB, so we stack it M3 on top of MB in order to have the similar voltage on the drain. So V X and Y, by having this kind of a high swing cascode device, ensure that Vx node voltage and Vy node voltage is similar, so that the I1, I2 and IB is similar, can be similar, right? So if you have a different drain voltage, you know that there is current mismatch. So this is a way of minimize the current mismatch, right? Minimize current mismatch. Current mismatch. Okay. So now the question is how we generate VB. That is something that we already learned from the high swing cascode biasing scheme, so you can refer that the technique. Okay. So this one ensure that so that finally ensure that a large output swing range. So this one then small swing range. For the source follower shown on the left, we know the current source on the bottom can be used, can be implemented by current meter. But for the input bias, we know we have to make sure that the input common mode should be properly well defined, ensure that M1 and M2 both in saturation. Easiest way to ensure that is that the bias the gate voltage to VDD by connecting large resistor there, so that this voltage is same at the VDD, and then we add the AC coupling capacitor, so the signal coming in on top of the VDD. So Vx node. So Vin can have any common mode bias voltage. So the Vx will be like a VDD here, and around the VDD signal will move up and down. Okay, do you know how much it can go up? The maximum peak swing can be allowed. You can imagine that if this gate voltage go up too high, then M1 will get into triode region. So the maximum Vx, so max amplitude, max Vin, Vx will be what? So VDD. So this one is overdrive voltage of this guy. Let's say, for example, VTH plus overdrive 1. So the drain voltage always VDD. So the maximum input would be VDD plus VTH, right? That's gonna be maximum Vx. So the maximum signal amplitude is limited by the VTH. Max V in amplitude equal VTH. Okay. For the lowest peak limit would be, let's say, so here VDD. So maximum would be maximum Vx range. Vx range is that we found that max is what? So max is VDD plus VTH. What about the minimum voltage? It can go down. Is that if this is going down too low, then this drain voltage of the M2 will be too low. So minimum requirement would be V overdrive 2 plus and VTH plus V overdrive 1, right? That's gonna be the minimum Vx voltage. But right now in this biasing scheme, the signal sitting on the bias sitting on the VDD voltage level, so the maximum allowable thing is still limited, the VTH. Okay, up and down VTH without having a distortion. So if you really want to maximize the output swing range, then you might need to place your output signal biasing voltage somewhere in the middle of the output range. Okay. So this is some example of a cascading amplifier. We have the common source amplifier. This is source follower. In this common source amplifier, depending on the bias current level, the Vx node voltage will change a lot, right? So it will affect the biasing point on the right hand side, the source follower. So this is the DC coupled, so it can pass from DC to all the way down to DC. But for the AC coupling on the right hand side, signal frequencies, this is the high pass filtering, right? Each cutoff frequency would be 1 over RCC, right? So the signal frequency must be beyond this, higher than this bandwidth, high pass filter bandwidth. But by having AC coupling here, we can independently bias the common source amplifier stage, meaning the output common mode range can be anything, right? Output common mode range does not affect the source follower stage, right? So this kind of thing give us the design freedom, right? But this is the design trade-off. If your application need to cover the DC all the way down to very low frequency DC, then you have to use this kind of DC coupled interface. But if your signal range is above certain voltage, certain frequency, then you can add as that the capacitor like shown in here. Okay. In the differential pair amplifier or buffer, anything, typically we cascade the same structure over and over. In that case, input common mode, input signal range and output signal range are the same, right? So you have to properly choose the input common mode range and input common mode and output common mode, right? In this scheme. So you have to make sure that for the common mode and signal swing range, all the devices in saturation, right? So all device in saturation. Suppose that let's calculate the signal range, for example. So this output, for example, one output node can go up to VDD. The maximum voltage will be VDD. So let's say Vx and Y. So Vx or Vy, the maximum voltage would be VDD. What about the minimum voltage? It can go down. For example, if this output drain voltage will be minimum when the input is at maximum. As you can see, the maximum input voltage here, this maximum is VDD, so the output of one stage would be going into the input of the other stage. So the maximum input voltage also VDD. So if that is VDD, the drain voltage will be minimum. In that case, how low it can go down to ensure that M2 is in saturation? That would be VDD minus VTH, right? So the Vx and Y signal range would be VDD and VDD minus VTH. So as you can see, for this kind of differential circuit, if you want to ensure that everything is in saturation, its swing range is limited by the VTH, right? So your biasing point would be, output common mode biasing would be somewhere between VDD minus VTH over 2, right? So that the signal can move up and down around that range. In that case, in some cases, this kind of a differential pair used in the clock buffer. So for in some case, if you raise, so for ensuring everything in saturation, the signal range would be limited, so VDD minus VTH. But if you don't care about the saturation or triode region, so you can have some large voltage swing, even though the M1 is in M1 and M2, or transistor differential pair transistor in saturation, you can sometimes endure that. So you can allow that for like clock buffering. If you really want the high swing signal, then you cannot do anything about it. You may push your input device in triode region. In that case, the current will steer onto left hand side and right hand side alternatively, by having some alternating clock input or signal here. You may have like this and have like this, right? So cascading stage in diff pair, amplitude, signal range, signal amplitude range, single-ended, for example, single-ended, and the swing, peak to peak swing, peak to peak swing is limited to VTH for for all devices in saturation. Okay, so if you don't wanna satisfy this sometime, as I explained, for clock buffering, you may allow that the input device in triode region, so that the input device is just work as a switch, digital switch, right? Like this. In triode. Okay.